There's a place in space where time stops, where space itself is torn apart, where the laws of physics break down completely. It's not theoretical, it's not science fiction, it's real. We call them black holes, and they're the most extreme objects in the universe. If you fell into one, you'd be stretched like spaghetti. Time would slow down for you while the universe outside aged billions of years. You'd see the entire future of the cosmos flash before your eyes in your final moments, and then you'd vanish. Everything that makes you, your memories, your thoughts, your atoms would be crushed to infinite density, a point smaller than anything imaginable. Or maybe not. Maybe something stranger happens. Maybe black holes are tunnels to other universes. Maybe they're the ultimate quantum computers. Maybe they hold the key to understanding reality itself. We've discovered thousands of black holes. We've photographed them. We've detected their gravitational waves rippling through space. We've watched them devour stars and galaxies. But we still don't understand what happens inside them. We don't know what they really are. We don't know if anything survives the fall. This is the story of humanity's quest to understand the universe's most mysterious objects, the things that shouldn't exist, but do. The places where physics goes to die. Welcome to the edge of everything. The inescapable prison. Let's start with the basics. What exactly is a black hole? Imagine taking the sun and crushing it down to the size of a city. Then keep crushing. Smaller than a house, smaller than a car, smaller than a marble. Eventually, you reach a point where the gravity becomes so intense that nothing can escape. Not matter, not light, not information, nothing. That's a black hole. It's a region of space where gravity is so strong that the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. The boundary of a black hole is called the event horizon. It's not a physical surface you could pass through it without feeling anything special, but once you cross that boundary, you're done. There's no coming back. Think of it like a waterfall. Above the falls, you can swim in any direction, but there's a point where the current becomes too strong. Once you pass that point, you're going over the edge no matter what you do. The event horizon is like that point, but for space itself. Inside the event horizon, all paths lead to the center, the singularity. You can try to turn around, fire rocket engines, do whatever you want. Doesn't matter. Space itself is falling into the singularity faster than light, carrying you with it. This sounds impossible. How can space itself fall? How can gravity be so strong that light can't escape? The answer comes from Einstein's theory of general relativity. Gravity isn't a force pulling things together. It's the curvature of space-time itself. Massive objects bend space-time around them, and things move along those curves. A black hole bends space-time so extremely that it curves back on itself. The fabric of space becomes so warped that all directions point inward. Up, down, left, right, forward, back, they all lead to the singularity. It's like being inside a sphere where every direction is down. There's no escape because there's no direction that leads out. The singularity at the center of every black hole is the singularity. This is where all the mass is concentrated. But here's the thing. We don't actually know what a singularity is. We know what the math says: infinite density, infinite curvature of spacetime. All the mass compressed to a point with zero volume. But infinite density doesn't make physical sense. It's a sign that our theories break down. General relativity predicts singularities. But general relativity also tells us it stops working at singularities. So what's really there? We don't know. Maybe the singularity is actually a quantum object, incredibly small, but not infinitely small. Maybe quantum effects prevent true infinite density. Maybe there's a tiny, ultra-dense core governed by quantum gravity, a theory we haven't figured out yet. Or maybe singularities are truly infinite. Maybe reality has genuine infinities at its core. That's philosophically disturbing, but not impossible. Some theorists suggest singularities might not exist at all. Maybe when you fall into a black hole, you don't hit a singularity, you pass through to another universe. Or you get quantum tunneled to some other location. Or something else we haven't imagined. The honest truth is, nobody knows. We can't observe singularities because they're always hidden behind event horizons. We can't send probes because nothing comes back. We can't visit because you die. Singularities are where physics goes from we're not sure to we have no idea. They're the ultimate mystery. Locked away, where we can never examine them directly. How black holes form. Black holes aren't rare. There are probably tens of millions in our galaxy alone, hundreds of billions in the observable universe. Most form from dying stars. Here's how. A massive star at least 8 times the sun's mass spends its life fighting gravity. Nuclear fusion in the core produces outward pressure that balances gravity's inward pull. The star is in equilibrium. But eventually, the star runs out of fuel. Fusion stops. The outward pressure disappears. Gravity wins. The star's core collapses in less than a second. Trillions of tons of matter falling inward at nearly the speed of light. The collapse is so violent that it triggers a supernova. The outer layers explode outward, while the core implodes. If the core is massive enough, more than about 3 times the sun's mass, nothing can stop the collapse. No known force can resist. The core shrinks past the point where it becomes a black hole. The event horizon forms. The singularity appears. From outside, you'd see the supernova explosion, but hidden in the center, where the star's core used to be, there's now black hole, a stellar mass black hole, typically 10 to 100 times the mass of the sun. These stellar black holes are the most common type, but they're not the only type. At the centers of most galaxies, including our own Milky Way, there are supermassive black holes millions or billions of times the sun's mass. We don't fully understand how these form. They're too big to come from single stars. Maybe they grew by swallowing gas and stars over billions of years. Maybe they formed from the direct collapse of enormous gas clouds in the early universe. Maybe they merged from many smaller black holes combining. Probably all of the above. There might also be intermediate mass black holes, between stellar and supermassive. We've found hints of these, but haven't confirmed many. And theoretically, there could be primordial black holes, tiny black holes formed in the Big Bang itself, ranging from microscopic to mountain-sized. We haven't found any, but they might exist. Black holes form when gravity becomes unstoppable, when matter is compressed so much that nothing can prevent complete collapse. And once formed, they're essentially eternal. They can grow by swallowing more matter, but they never shrink, at least, not noticeably, until Stephen Hawking discovered something that changed everything. Hawking radiation. In 1974, Stephen Hawking made a shocking discovery. Black holes aren't completely black. They emit radiation, very slowly, very faintly, but real radiation. This is called Hawking radiation, and it's one of the most important discoveries in theoretical physics. Here's the simplified version of how it works. Empty space isn't actually empty. Quantum mechanics tells us that even in vacuum, particle-antiparticle pairs constantly pop into existence and immediately annihilate. These are called virtual particles. Near the event horizon of a black hole, something strange happens. Sometimes a virtual pair appears right at the boundary. One particle falls into the black hole, the other escapes into space. The escaping particle becomes real. It's now Hawking radiation. The particle that fell in has negative energy relative to the black hole. When it's absorbed, the black hole loses a tiny bit of mass. Over time, enormous amounts of time, the black hole evaporates. It radiates away its mass particle, I particle, until eventually, it vanishes completely. For stellar mass black holes, this takes unimaginably long. A black hole the mass of our sun would take 10 to the 67th years to evaporate. That's a trillion years. The universe is only 14 billion years old, so stellar black holes will be around essentially forever. But smaller black holes evaporate faster. A black hole the mass of a mountain would evaporate in the age of the universe, and at the end, as it gets smaller and smaller, it would glow brighter and brighter, finally exploding in a burst of radiation. We've never seen this happen, but the theory is solid, and it reveals something profound. Hawking radiation shows that black holes have temperature. They radiate like hot objects. This means they have entropy, a measure of disorder and information content. But here's the puzzle. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is weird. For normal objects, entropy relates to volume. More stuff means more entropy. For black holes, it's about surface area. It's as if all the information about what fell into the black hole is somehow encoded on its two-dimensional surface rather than in its three-dimensional interior. This led to the holographic principle, the idea that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional boundary. Reality might be a hologram. We'll come back to that mind-bending idea later. But first, let's talk about what happens if you actually fall into a black hole. The infalling observer, imagine you're falling into a black hole. What do you experience? First, as you approach, you'd notice tidal forces. These are differences in gravitational pull. The side of your body closer to the black hole feels stronger gravity, and the far side. For a supermassive black hole, tidal forces are gentle near the event horizon. You'd cross it without feeling anything special. But for a stellar mass black hole, tidal forces are extreme. You'd be stretched lengthwise and compressed sideways spaghettify. Long before you reach the event horizon, let's assume you're falling into a supermassive black hole and somehow survive. You cross the event horizon. What now? From your perspective, nothing dramatic happens at the boundary itself. You don't feel a surface. Space looks normal around you. You can see out into the universe, but you can't communicate out. Any signal you send, light, radio, whatever, gets dragged inward with you. From outside, you've vanished. Your signals never escape. As you fall deeper, tidal forces strengthen. Eventually, they'd tear you apart. But before that, you'd see something amazing. Looking outward, you'd see the universe blue-shifted and accelerated. Time outside appears to speed up. Stars age rapidly. The universe evolves before your eyes. In principle, as you approach the singularity, you'd see the entire future of the universe flash past in seconds or less. You'd watch stars burn out, galaxies fade, the universe darken and die, all compressed into your final moments. Then you'd hit the singularity. And that's where we genuinely don't know what happens. The laws of physics break down. Our theories stop working. You might be crushed to infinite density, or you might pass through to another universe, or experience something we can't describe with current physics. From outside, none of this is visible. Once you cross the event horizon, you're gone from our universe's perspective. You've left the observable cosmos, but you're still falling, still experiencing. Until the singularity, whatever happens there is perhaps the deepest mystery in physics. Act 2. Observing the invisible, finding black hole. If black holes are invisible, how do we know they exist? For decades, black holes were purely theoretical. Einstein's equations predicted them in 1916. But most physicists, including Einstein himself, thought they were mathematical curiosities that didn't exist in nature. That changed in the 1960s. Astronomers discovered X-ray sources in space objects emitting enormous amounts of high-energy radiation. Some of these sources were binaries, a visible star orbiting an invisible companion. By watching how the visible star moves, astronomers could calculate the mass of its companion. In some cases, the companion was far too massive to be anything but a black hole, too massive for a neutron star, too compact to be a visible star. And it emitted X-rays from matter heating up as it fell toward the invisible object. Cygnus X1 was the first strong candidate, discovered in 1964 and confirmed as likely a black hole in the 70s. Stephen Hawking bet physicist Kip Thorne that it wasn't a black hole. Hawking lost the bet in 1990 when evidence became overwhelming. Since then, we've found thousands of black holes. We've developed multiple techniques. We watch stars orbiting invisible companions and calculate the companion's mass. If it's too massive to be anything else, it's probably a black hole. We detect X-ray emissions from accretion disks, matter spiraling into black holes, heating to millions of degrees and radiating X-rays. We observe jet beams of particles and radiation shot out perpendicular to accretion disks, powered by black hole spin and magnetic fields. We measure gravitational lensing light from background objects spent by black hole gravity, creating distorted images. And most recently, we've detected gravitational waves, ripples in spacetime produced by black holes colliding and merging. Each technique reveals different black holes. X-ray observations find stellar mass black holes feeding on companion stars. Motion of stars in galactic centers reveals supermassive black holes. Gravitational waves detect black holes anywhere in the universe, even in empty space where they're otherwise invisible. We've gone from 0 confirmed black holes to thousands in just a few decades, and we're getting better at finding them all the time. The supermassive monster at our galaxy's heart, at the center of our Milky Way galaxy, 26,000 light-years from Earth, there's a supermassive black hole called Sagittarius A star, abbreviated SCR A star. It's 4 million times the mass of the Sun, and we've watched stars orbit around it. For decades, astronomers tracked individual stars near the galactic center. One star, called S2, completes an orbit every 16 years. At closest approach, it reaches 17% the speed of light, 50,000 kilometers per second. By watching S2 and other stars orbit this invisible point, astronomers proved beyond doubt that something massive and compact sits there. The only explanation is a supermassive black hole. In 2020, physicist Roger Penrose won the Nobel Prize partly for this work, proving that real black holes exist in the universe, not just in theory. But Star isn't unique. Almost every large galaxy has a supermassive black hole at its center. Some are millions of times the sun's mass, others are billions. The most massive known black hole is in the galaxy TUN 618.66 billion times the sun's mass. Its event horizon is about 11 times the size of Neptune's orbit. It's so massive that calling it a black hole almost seems inadequate. It's more like a black monster. These supermassive black holes shape their galaxies. When matter falls into them, enormous energy is released, sometimes more than all the stars in the galaxy combined. This energy can blow gas out of the galaxy, stopping star formation, or it can compress gas, triggering new star formation. There's a relationship between the mass of a galaxy's central black hole and properties of the galaxy itself, like the speeds of stars in the galactic bulge. This suggests black holes and galaxies grow together, influencing each other's evolution. How supermassive black holes formed is still mysterious. They were already massive in the early universe, just a billion years after the Big Bang. That's not much time to grow from stellar mass black holes to billions of solar masses. Maybe they formed from direct collapse of enormous gas clouds. Maybe primordial black holes from the Big Bang served as seeds. Maybe they grew by merging with many other black holes in dense star clusters. Whatever the mechanism, supermassive black holes are now a key part of how galaxies work. They're not just passive objects sitting in galactic centers. They're active participants in cosmic evolution. And in 2019, we finally photographed one. The first image on April 10, 2019. The Event Horizon Telescope collaboration released the first direct image of a black hole. Not an artist's impression, not a simulation, an actual photograph of the shadow of a black hole against glowing gas. The target was an 87 star, the supermassive black hole at the center of the galaxy, and 55 million light-years away. It's 6.5 billion times the mass of the sun. The image shows a bright ring of light surrounding a dark circle. The dark circle is the black hole's shadow, the region where light either falls into the black hole or is so strongly bent that it doesn't reach us. The bright ring is the photon sphere where light orbits the black hole before either escaping or falling in. Behind the black hole, there's glowing gas heated to billions of degrees as it spirals inward. Some of that light is bent around the black hole by gravity, creating the bright ring we see. The bottom of the ring is brighter than the top. This is because the gas orbits the black hole at relativistic speeds near the speed of light. The side spinning toward us appears brighter due to relativistic beaming and Doppler effects. The side spinning away is dimmer. Creating this image was an incredible technical achievement. Black holes are small even in 87 stars event horizon, though huge by solar system standards. Subtends a tiny angle in the sky from Earth. Resolving it required a telescope the size of Earth. The Event Horizon Telescope is exactly that. A network of radio telescopes around the world, all observing simultaneously. By combining data from telescopes in Hawaii, Arizona, Spain, Chile, Mexico, the South Pole, and elsewhere, astronomers created a virtual telescope the diameter of the planet. The technique is called Very Long Baseline Interferometry. It requires incredibly precise synchronization using atomic clocks and careful calibration to account for Earth's rotation, atmospheric effects, and instrumental variations. Even then, the telescopes don't create a complete picture. They sample tiny pieces of the image, and sophisticated algorithms fill in the gaps to reconstruct what the black hole looks like. The result: an image that matches predictions from general relativity remarkably well. The size of the shadow, the shape of the ring, the brightness distribution, all consistent with theory. In 2022, the collaboration released a second image, Sagittarius A star, our own galaxy's black hole. This was harder because Star is much smaller and varies rapidly, so data from different telescopes had to be carefully synchronized. But again, the image matched theory. The shadow is there. The bright ring is visible. General relativity works even in the most extreme conditions we can observe. These images are more than pretty pictures. They're tests of general relativity, is strong gravity. They're probes of the environment near event horizons. They're confirmation that black holes are real and behave as predicted. And they're just the beginning. Future observations will create movies of black holes, showing how gas flows and magnetic fields evolve over time. Gravitational waves on September 14, 2015. Two black holes collided in a distant galaxy, 1 and 3 billion light-years away. Each was about 30 times the mass of the Sun. They'd been orbiting each other, gradually spiraling inward as they lost energy to gravitational wave radiation. In their final moments, they whipped around each other at half the speed of light, orbiting hundreds of times per second. Then they merge, forming a single black hole 60 times the Sun's mass. The collision released more energy than all the stars in the observable universe combined. For a brief instant, that energy was carried away by gravitational waves. Those waves spread outward at the speed of light, rippling through the fabric of spacetime itself. They crossed intergalactic space for over 1 billion years. And on September 14, 2015, they reached Earth. Two detectors, one in Louisiana, one in Washington state, registered the signal within milliseconds of each other. Each detector consists of two 4-kilometer-long arms arranged in an L shape. Laser beams bounce back and forth in each arm, and interferometry detects tiny changes, arm length caused by passing gravitational waves. The signal lasted less than half a second, but it was clear and matched theoretical predictions perfectly. The frequency and amplitude evolution told the story. Two massive objects spiraling together and merging. This was the first direct detection of gravitational waves, predicted by Einstein a century earlier but never previously observed. It was also the first direct observation of a black hole merger. The discoverers Rainer Weiss, Barry Barish, and Kip Thorne won the Nobel Prize in 2017. Since then, dozens more gravitational wave events have been detected. Most are black hole mergers. A few are neutron star mergers. The detections reveal a hidden population of black holes we couldn't see any other way. Gravitational wave astronomy is now field. Future detectors will be even more sensitive. The Laser Interferometer Space Antenna LISO, planned for the 2030s, will be a space-based detector capable of observing supermassive black hole mergers. Across the universe, gravitational waves let us hear black holes. Combined with electromagnetic observations, telescopes seeing light, X-rays, radio waves, we can study black holes in unprecedented detail. We're entering a golden age of black hole astronomy. What we've learned after decades of observation. Here's what we know about black holes. They're real. Not theoretical curiosities, but actual objects that exist throughout the universe in enormous numbers. They come in sizes ranging from a few times the Sun's mass to billions. The biggest ones sit at the centers of galaxies and shape cosmic evolution. They're powered by accretion matter falling in. As matter spirals inward, friction heats it to billions of degrees, releasing enormous energy as X-rays and other radiation. They can launch jet beams of particles and radiation that extend thousands or millions of light-years into space. These jets are powered by black hole spin and magnetic fields spreading the accretion disk. They merge. Black hole collisions are common enough that we detect them regularly. Each merger releases energy through gravitational waves and creates a single larger black hole. They evaporate very, very slowly. Hawking radiation means black holes aren't eternal. Though stellar mass and larger black holes will outlast the universe's current age many times over, they have temperature and entropy. This connects black holes to thermodynamics and information theory in ways we're still trying to understand. But despite all we've learned, fundamental mysteries remain. What happens at the singularity? What happens to information that falls in? Can anything ever escape? Could black holes be portals to other universes? These questions bring us to the strangest and most speculative territory in black hole physics. Act 3. Impossible physics. The information paradox. In the 1970s, Stephen Hawking created a crisis in physics. Not intentionally, but his discovery of black hole radiation led to a paradox that still hasn't been fully resolved. Here's the problem. Quantum mechanics says information cannot be destroyed. If you know the complete state of a system now, you can in principle calculate its state at any past or future time. Information is conserved, but black holes seem to destroy information. If you throw a book into a black hole, all the information in that book, every word, every molecule, every quantum detail falls through the event horizon. From outside, it's gone. Hawking radiation doesn't help. The radiation is thermal random. It doesn't carry information about what fell into the black hole. If you tried to reconstruct what fell in from the radiation coming out, you couldn't. The information seems lost. So when a black hole evaporates completely, The information that fell in appears to vanish from the universe. This violates quantum mechanics. You can't destroy information. Something has to give. Either quantum mechanics is wrong, general relativity is wrong, or our understanding of black holes is incomplete. Physicists have debated this for 50 years. Many proposals exist. Maybe information is encoded in subtle correlations in Hawking radiation that we haven't figured out how to detect. Maybe the final moments of black hole evaporation are special. The last burst of radiation carries all the information in a quantum scrambled form. Maybe black holes have hair structures around the event horizon that store information. Maybe information falls into another universe through the singularity. Maybe the event horizon isn't quite what we think. Maybe it's fuzzy or has other properties that let information escape. Or maybe information really is destroyed, and quantum mechanics needs modification. In extreme gravity, the paradox shows that black holes sit at the intersection of quantum mechanics and general relativity to theories that don't fit together. Solving the paradox probably requires quantum gravity, a theory we don't yet have. Wormhole science fiction loves wormhole shortcuts through space and time, connecting distant parts of the universe, and they're real. Sort of. General relativity allows solutions where space-time is connected in non-trivial topology, creating bridges between distant regions or even different universes. The most famous is the Einstein-Rosen bridge. The equations show that a black hole's space-time geometry naturally extends to create a tunnel connecting to another region. In principle, you could enter a black hole and emerge somewhere or someone else. There are problems, though. First, Einstein-Rosen bridges collapse incredibly quickly. You'd need to travel faster than light to get through before the tunnel pinches off, and nothing travels faster than light. Second, to keep a wormhole open, you'd need exotic matter with negative mass or negative energy density. This violates the usual energy conditions in general relativity. We've never observed exotic matter, and it's unclear if it can exist. Third, even if you could travel through, you'd probably be destroyed. The tidal forces and radiation inside a wormhole would be extreme. Any matter entering would likely destabilize the wormhole, causing it to collapse. But mathematically, they're possible, and some solutions are traversable, stable enough for objects to pass through. Could advanced civilizations create artificial wormholes? Could natural wormholes exist, perhaps formed in the early universe when conditions were extreme and exotic matter might have existed? We don't know. We've never observed a wormhole. We don't know if they're physically possible or just mathematical curiosities, but if they exist, they'd revolutionize everything. Instant travel across the universe, shortcuts through time, possibly allowing time travel into the past. Access to other universes if the wormhole connects to them. The physics says maybe. The technology to create one is far beyond us. The question of whether they naturally exist remains open. Time travel black holes mess with time in strange ways. Near the event horizon, time slows down relative to observers far away. This is called gravitational time dilation. If you hovered just outside the event horizon of a black hole while your friends stayed far away, you'd age slowly while they age quickly. An hour for you might be years for them. This isn't science fiction. It's real, measurable, and a consequence of general relativity. GPS satellites have to account for time dilation to work accurately. Black holes take time dilation to extremes. The closer you get to the event horizon, the more extreme the effect. At the horizon itself, time dilation becomes infinite. From outside, an infalling object takes forever to cross the horizon. Its clock slows to a stop. Of course, from the infalling object's perspective, time passes normally. It crosses in finite time. The asymmetry is because different observers experience time differently near extreme gravity. Could you use this for time travel? Sort of. You could orbit close to a black hole for a while, then leave. You'd have aged less than people far from the black hole. You've traveled to their future. This is forward time travel, and it's uncontroversial. We know it works. It's just impractical because you need extreme gravity or near light speeds. Backward time travel going to the past is much more problematic. General relativity does allow solutions with closed time-like curves, where you could travel into your own past. Some rotating black hole solutions curve black holes have regions where closed time-like curves exist. In principle, you could travel through the rotating black hole's interior and emerge in your own past, but this requires passing through the ring singularity inside a rotating black hole without being destroyed. it probably also requires negative energy and exotic matter. And it raises paradoxes. What if you kill your grandfather before your parent is born? Most physicists think backward time travel is impossible, despite what the equations technically allow. There's probably some as-yet-unknown law of physics, a chronology protection conjecture, as Stephen Hawking called it, that prevents closed time-like curves from forming. But we don't know for sure. And black holes remain the most plausible, if still implausible, mechanism for time travel. White holes. If black holes are regions you can enter but never leave, could there be opposite objects, white holes, regions you can leave but never enter? Mathematically, yes. The equations of general relativity that produce black holes also predict white holes. They're time-reversed black holes. A white hole would be a region of spacetime that expels matter and energy. Nothing could fall in. Everything would be pushed out. From outside, you'd see stuff erupting from the white hole, the opposite of a black hole swallowing things. The event horizon of a white hole would be a barrier you couldn't cross inward. You could leave, but you couldn't enter or return. Do white holes exist? Almost certainly not. They're unstable. The slightest perturbation would destroy them, and they violate the second law of thermodynamics. Entropy would decrease, which doesn't happen in our universe. Some speculate that the Big Bang might have been a white hole, a point from which the universe emerged, but this is highly speculative and not supported by evidence. Others suggest that when black holes evaporate completely via Hawking radiation, they might explosively transform into white holes, expelling their contents. This is even more speculative. White holes are mathematical curiosities that probably don't exist in nature, but they're interesting because they show that the equations of general relativity have features we don't fully understand. The universe uses some solutions black holes, but apparently not others white holes. Why? What determines which mathematical possibilities become physical realities? The holographic principle. Remember how black hole entropy depends on surface area rather than volume. This leads to one of the strangest ideas in modern physics, the holographic principle. The idea is that all the information in a volume of space can be encoded on the boundary of that volume. Three-dimensional reality might be a projection of information stored on a two-dimensional surface, like a hologram. You shine light through a two-dimensional pattern and get a three-dimensional image. The 3D image is real in a sense, but all the information is actually in the 2D pattern. Maybe the universe works the same way. Maybe the three spatial dimensions we experience are projections of information encoded on a distant two-dimensional boundary. This sounds crazy, but it's taken seriously by many physicists, especially those working on string theory and quantum gravity. The clearest example is the ADS-CFT correspondence, a mathematical relationship between a theory of gravity in a higher dimensional space and a quantum field theory on the boundary of that space. The two theories are equivalent. Everything happening in the higher dimensional bulk can be described by equations on the lower dimensional boundary. If the holographic principle is true, it has profound implications. It means space might not be fundamental. The three dimensions we experience might be emergent, derived from something more basic. Reality at its deepest level might be two-dimensional, with the third dimension being a kind of illusion. It also suggests that the information paradox might be resolved if information falling into a black hole is encoded on the event horizon, the boundary. Then it's not truly lost. It's stored on the surface in a highly scrambled form, and eventually returned via Hawking radiation. Black holes become the ultimate quantum computers, objects that store maximum information for their size, encoded holographically on their surfaces. This is speculative. The holographic principle is well established in certain theoretical contexts, but not proven for our universe. But it's a leading candidate for understanding quantum gravity and the deep nature of spacetime. And it all comes from studying black holes, the most extreme objects in the universe, where physics gets weird and our theories are pushed to their limits. Act 4. To dark future. When stars die, black holes are eternal, right? Nothing escapes. They just keep growing. Not quite. Remember Hawking radiation. Black holes evaporate, though incredibly slowly. Let's project into the deep future and see what happens. Right now, the universe is 13.8 billion years old. Stars are shining. Galaxies are full of light and activity. Black holes exist but are outnumbered by stars. Fast forward to 100 billion years. Star formation is winding down. The universe has used up most of its hydrogen gas. New stars are rare. Most of the stars that will ever exist have already formed. By a trillion years, 1,000 times, the universe's current age star formation has essentially stopped. The longest-lived stars, tiny red dwarfs, are starting to burn out. Galaxies are fading. At 10 trillion years, all the red dwarfs are gone. No stars remain. Galaxies are now populated by dead stellar remnants, white dwarfs, neutron stars, and black holes. Planets have been ejected from their orbits or fallen into dead stars. Solar systems don't exist anymore. Everything drifts through darkness, but black holes endure. They're patient. They've swallowed billions of stars over the eons and grown massive. The supermassive black holes at galactic centers are now the dominant objects, each surrounded by orbiting dead stars and stellar black holes. And the universe keeps expanding, driven by dark energy. Galaxies move apart. Eventually, every galaxy is isolated, alone in its own expanding bubble of space, unable to see any other galaxy. Each becomes a cosmic island. Within each island, gravity still works. Dead stars continue orbiting the central supermassive black hole. Over unfathomable timescales, these orbits decay. Stars emit gravitational waves as they spiral inward. Eventually, everything falls into the central black hole. By 10 to the 37th years, that's 10 trillion years. Most matter in each galaxy has fallen into the central black hole. Each former galaxy is now a single black hole floating in empty space. The universe is dark, cold, and almost empty. Just black holes separated by exponentially expanding voids. But the story's not over. Black holes evaporate. The era of black holes. In the era of black holes, the universe consists almost entirely of black holes floating in expanding emptiness. How long does this last? It depends on black hole size. A solar mass black hole evaporates in 10 to the 67th years. The supermassive black holes, millions to billions of solar masses, take much longer. A billion solar mass black hole needs 10 to the 100th years to evaporate. During this time, black holes are the most interesting objects in the universe. They're the last sources of energy and activity. Hawking radiation from black holes might be the only thing happening. Could life exist during the black hole era? Probably not. Biological life. Stars and planets are gone. But maybe something based on different principles, structures made of magnetic fields or information patterns. Civilizations living on the surfaces of black holes, powered by Hawking radiation. This is wild speculation that the universe will spend far more time in the black hole era than in the current era of stars and galaxies. If consciousness ever exists during that time, it would be utterly alien to us. Eventually, even the largest black holes evaporate. One by one, they shrink. As they get smaller, Hawking radiation intensifies. In their final moments, they glow bright, radiating away their last mass in a burst of particles, and then they vanish. By 10 to the 106th years, the last black holes have evaporated. Nothing remains, a particle spreading through endless space. The universe has reached maximum entropy. Heat death. The era of black holes is over. Beyond heat death, after heat death, what's left? Mostly photons, light that's been redshifted to near zero energy by cosmic expansion, and maybe some stable particles like electrons and positrons, protons if they haven't decayed. Space keeps expanding, driven by dark energy. The temperature approaches absolute zero. Nothing happens. No energy flows, no information processes, no complexity. This is the heat death of the universe. Not an explosive end, but a gradual fade to emptiness and stillness. It's depressing. Everything that ever existed, stars, planets, life, civilizations, black holes, all gone. Reduced to dilute gas spreading through infinite space. But there might be surprises. Some theorists speculate that after exponentially long times, quantum fluctuations might create new structures. Not likely, not soon, but given infinite time, improbable things eventually happen. Maybe new universes spontaneously nucleate from quantum vacuum fluctuations. Maybe we're in a vast landscape of universes, constantly forming and dissolving. Or maybe dark energy isn't constant. If it decays or changes, the universe's fate changes. Expansion might slow, or accelerate faster, or reverse, leading to a big crunch or everything collapses back together. We don't know. Dark energy is mysterious. We observe its effects, but don't understand what it is or whether it's stable. The far future is uncertain, but based on current understanding, Heat death seems inevitable. The universe will end not with a bang but with endless cold and silence. Black holes, ironically, are the last interesting things. After they're gone, nothing remains but expanding emptiness. What black holes teach us? Why study black holes and the universe's far future? It seems abstract and disconnected from life, but black holes teach fundamental lessons about reality. They show that space and time are flexible, dynamic, part of the universe rather than a stage it plays on. Near black holes, time slows, space curves, the fabric of reality warps dramatically. They show that our intuitions about reality break down in extreme conditions. Nothing should be able to trap light. Nothing should curve space infinitely, yet black holes do both. They show that gravity, seemingly the weakest force, dominates on cosmic scales and creates the universe's most extreme phenomena. They reveal connections between seemingly unrelated areas of physics. Black holes link gravity, quantum mechanics, thermodynamics, and information theory. Solving black hole mysteries requires understanding how these fields fit together. They force us to confront deep questions. What is information? What is time? What happens to matter under infinite compression? Can anything truly be destroyed? And they humble us. Black holes demonstrate that the universe contains phenomena far beyond everyday experience. We're not entitled to understand everything through common sense. Reality is stranger than we naturally expect. The universe's far future also teaches lessons, mainly about perspective and significance. In the long run, the really long run, nothing lasts. Stars, galaxies, black holes, everything eventually fades. The universe trends toward emptiness and silence. Does this make everything meaningless? Some philosophers say yes. Others say no, meaning exists in the present, in experience and relationships and creation, not in permanence. From a cosmic perspective, human civilization is a brief flicker, but we're the brief flicker that can understand black holes, calculate the universe's fate, and contemplate our own cosmic insignificance. That's something. Maybe even something special. Could we survive? Humanity won't see the universe's heat death. We'll be long gone by then, one way or another. But could an advanced civilization survive for billions of years? Could consciousness persist to witness the far future? It's barely possible, though incredibly difficult. In the near-term next few billion years, the main threat is our sun. In 5 billion years, the sun will expand into a red giant, engulfing Earth's orbit. We'd need to move elsewhere. Mars becomes habitable for a while during this period. The outer solar system moons might become comfortable, but eventually, the sun dies, and the solar system becomes uninhabitable. A sufficiently advanced civilization could travel to other stars, colonize new systems, spread across the galaxy. As each star dies, move to the next. This buys billions of years. But eventually, all stars die. By 100 trillion years, no stars remain. A civilization would need to survive on energy sources other than stellar fusion. Black holes become important. A civilization could extract energy from black holes through the Penrose process, stealing rotational energy from a spinning black hole, or by dropping matter into a black hole and harvesting the energy released. This could sustain a civilization for fantastically long times, far longer than the stellar era. You could build structures around black holes, living off their energy as they slowly evaporate. But eventually, the black holes evaporate too. By 10 to the 100th years, even this energy source is gone. Is there anything beyond? Could consciousness exist in the heat-death era? Maybe, if consciousness can exist as pure information without physical structures. Quantum fluctuations in the vacuum might briefly create information processing structures. Consciousness might exist intermittently, sporadically, as the universe randomly fluctuates into states capable of thought. This is speculative to the point of fantasy, but technically possible given infinite time and quantum uncertainty. Alternatively, maybe escape is possible. Create a new universe and move into it, or exploit wormholes to reach younger universes elsewhere in the multiverse, or modify local physics to prevent heat death in your region. These require technologies so advanced they're indistinguishable from magic, but they're not ruled out by known physics. The universe's fate seems grim, but consciousness is resourceful. Maybe something survives, maybe something persists, or maybe not. Maybe consciousness is temporary, a brief phenomenon in a universe mostly devoid of it. Either way, we're lucky to exist now, in the era of stars and galaxies, when the universe is interesting and habitable. That won't last forever, but it lasts now. And that's enough. Act 5. The ultimate questions: do we live in a black hole? Here's a weird idea. Maybe our entire universe is inside a black hole. Think about it. From inside a black hole, you can't see out. You can't escape. Space expands toward the singularity. Our universe has similar properties. We can't see beyond the cosmic horizon, the boundary set by light travel time since the Big Bang. We can't escape the universe. Space is expanding. Could the Big Bang have been entry into a black hole? Could the cosmic horizon be an event horizon viewed from inside? Some physicists take this seriously. The math is suggestive. A black hole's interior, according to certain solutions of Einstein's equations, resembles an expanding universe. If we're inside a black hole, that black hole exists in some parent universe. Maybe that universe also exists inside a black hole in an even larger universe. It's black holes all the way down an infinite nested hierarchy. Or maybe our universe is a black hole that formed from matter collapsing in a parent universe. When a star collapses in our universe, maybe it creates a new baby universe inside the black hole, where physics starts over with new laws. This would mean every black hole we observe spawns a new universe. And we live in a universe spawned from a black hole in a parent cosmos. It's cosmic reproduction universes giving birth to other universes through black hole formation. This is speculative but not crazy. It's called cosmological natural selection, proposed by physicist Lee Smolin. If universes that produce lots of black holes also produce lots of baby universes, then over many generations, universes evolve to produce black holes efficiently. The parameters of physics might be selected for black hole production. Life might be a side effect. We exist because the physics that allows life also allows stars. And stars create black holes when they die. Can we test this? Not easily. We can't observe the parent universe or baby universes, but we could check if our universe's physical constants are optimized for black hole production. So far, results are mixed. It's a fascinating idea, though. Black holes might be more than just endpoints of stellar evolution. They might be seeds of new universes, making them the most important objects in existence. Information and reality. Let's return to the information paradox. Not just as a puzzle, but as a clue about the nature of reality. If black holes preserve information on their surfaces holographically, what does that tell us? Maybe reality is fundamentally informational, not made of matter and energy, but made of information. Matter and energy are how information manifests. This is a radical idea. We're used to thinking of information as abstract patterns, meanings, relationships. Physical things seem more real, more fundamental, but quantum mechanics hints otherwise. Quantum states are information. They describe what's possible, what's probable. When you measure a quantum system, you gain information. The act of gaining information physically affects the system. Quantum entanglement is information shared between particles. You can't communicate faster than light using entanglement, but you can teleport. Quantum states transfer information from one place to another. Using entanglement and classical communication, black holes amplify these quantum information effects to cosmic scales. A black hole's entropy, its information content, is proportional to its surface area. De Bekenstein-Bound says, a region of space can hold only so much information, limited by its surface area. This suggests space itself is made of information. Maybe space-time isn't fundamental. Maybe it emerges from something deeper. Quantum information, entanglement patterns, bits of data woven together. The holographic principle says a volume's information is on its boundary. Maybe volume is an illusion. Maybe depth is emergent from two-dimensional information surfaces. If reality is information, then physics is computation. The universe processes information, evolving from one state to another according to laws that are ultimately computational. Consciousness might be special because it processes information subjectively. Physical systems process information mechanically. Conscious systems experience information. Black holes are the ultimate information processors. Maximally dense information encoded on event horizons, processed through Hawking radiation, implementing the most extreme computations possible. This is speculative, but it's where black hole physics leads. Toward a view of reality as information, computation, quantum entanglement woven into spacetime itself. What is time? Black holes also challenge our understanding of time. Near the event horizon, time slows relative to distant observers. At the horizon, time stops from outside. An infalling object takes forever to cross. Inside, Time and space swap roles. Time points toward the singularity. You can't avoid moving forward in time, so you can't avoid reaching the singularity. Trying to avoid the future is like trying to move backward in time, which is impossible. The singularity isn't a place, it's a moment. A moment when time bends for anything that falls in. What is time, really? Why does it flow in one direction? Why does the future feel different from the past? Physics doesn't have great answers. The laws of physics are mostly time-symmetric. They work the same forward or backward, yet we experience time as flowing from past to future, never the reverse. This asymmetry is called the arrow of time. It's related to entropy. The second law of thermodynamics says entropy increases, disorder grows. Broken eggs don't reassemble. Heat doesn't spontaneously concentrate. The past is order, the future disordered. Black holes fit this pattern. They increase the universe's entropy. When things fall into black holes, entropy goes up. When black holes evaporate, entropy goes up. They're entropy maximizers, thermodynamic sinks. Maybe time is fundamentally about entropy, about information flowing from ordered to disordered states. Maybe time emerges from the statistical behavior of information. Black holes, with their event horizons and singularities, are places where time behaves most strangely. Studying them might reveal time's true nature. Some physicists think time is emergent, not fundamental. At the deepest level, there's no time, just timeless quantum information. Time appears when you have many particles interacting, creating thermodynamic flows of entropy. If time is emergent, then the singularity where time ends might be where time emerges, dissolving back into timeless quantum foam. This is wild speculation, but black holes force us to confront what time means. And the answers are strange. Are black holes conscious? Here's the strangest question of all. Could black holes be conscious? This sounds absurd. Black holes are objects, not minds. They're concentrations of mass and gravity, not thinking beings. But remember panpsychism, the idea that consciousness is a fundamental property of matter, present in all things to varying degrees. If panpsychism is true, then everything has some minimal form of experience. Particles have particle-level experience. Complex systems, like brains, have complex experience. What about black holes? They're complex systems. They process information. They have entropy, which relates to information content. They interact with their environment. Could they have black hole-level experience? Some form of alien, incomprehensible consciousness? Probably not in any way we'd recognize. They don't have sensory input like we do. They don't think or decide or feel emotions. They're not self-aware, but maybe they have some internal state, some aspect of subjectivity that's as different from human consciousness as black hole physics is from everyday experience. This is impossibly speculative. We can't test it. We can't even define what it would mean for a black hole to be conscious. But it's interesting that black holes have properties usually associated with consciousness. They're complex. They process information. They have internal states hidden from outside observation. The event horizon is like the boundary of consciousness. Everything inside is private, inaccessible from outside. You can observe a black hole's mass and spin, but not its interior. Just like you can observe someone's behavior but not their inner experience. Maybe consciousness requires information integration of a specific type, and black holes don't have it. Maybe consciousness requires biological structures. Maybe it requires quantum coherence of particular forms. Or maybe consciousness is more universal than we think, and black holes, as the universe's most extreme information processors, have their own form of experience. We don't know. We can't know. But asking the question reveals how little we understand consciousness, and how strange black holes truly are. The meaning of it all after this journey through black holes, entropy, evaporation, and the heat death of the universe. What does it mean? Black holes are places where our physics breaks down. Where time ends, space curves infinitely, information might be destroyed, and quantum mechanics and gravity collide. They're laboratories for testing our deepest theories. Every observation of black holes tests general relativity, extreme conditions. Every paradox pushes us toward quantum gravity. They're also reminders of our limits. We can observe event horizons, but never see past them. We can calculate what happens at singularities, but our equations give infinities instead of answers. We know black holes exist but can't fully explain them. This is humbling. Despite centuries of progress, despite understanding atoms and galaxies and everything in between, we hit walls. Black holes are walls, boundaries beyond which our knowledge doesn't extend, but they're also inspiring. We've learned so much. We've photographed black holes, detected their gravitational waves, measured their effects on nearby matter, understood their role in cosmic evolution. We've projected billions of years into the future and seen the universe's fate. We've contemplated time, information, reality itself. Black holes force us to think deeply about fundamental questions. What is time? What is information? What survives? What doesn't? What is the universe's ultimate fate? These aren't just physics questions. They're philosophical questions. They affect how we think about meaning and significance. If nothing lasts, if black holes evaporate, the universe dies. Everything fades to nothing. Does anything matter? Maybe meaning is in the present, in experience and understanding while they exist. Maybe the fact that we exist now, can study black holes, can contemplate the cosmos, is meaningful regardless of the far future. Or maybe the universe's ultimate fate reveals something deeper. Maybe heat death isn't the end. Maybe new structures emerge. Maybe the cycle continues. We don't know. We're finite beings pondering infinite questions. We're collections of atoms studying the places where atoms are crushed to nothingness. That's profound. That's remarkable. That's worth doing. Black holes are extreme, alien, terrifying, and beautiful. They're the universe showing us its limits and inviting us to explore them. Final act. Where we go from here. Future observations. We've learned a lot about black holes, but we're just beginning. Future observations will reveal much more. The Event Horizon Telescope will continue improving. More radio telescopes join the network, increasing resolution. Observations at shorter wavelengths provide sharper images. Movies of black holes will show gas flowing, magnetic fields evolving, jets launching in real time. We'll observe more black holes, not just an 87 star Anscura star, but dozens of others. We'll see black holes of different masses and spins in different environments. We'll test whether they all match general relativity or if there are surprises. The Laser Interferometer Space Antenna LISA will launch in the 2030s. It's a space-based gravitational wave detector. 3 spacecraft flying in formation millions of kilometers apart. It'll detect supermassive black hole mergers across the universe, thousands of times more sensitive than ground-based detectors. This will reveal the merger history of supermassive black holes, how often they merge, how they grow, how they formed in the early universe. It might even detect the gravitational wave background, a hum of gravitational radiation from countless mergers throughout cosmic history. LISA might also detect primordial black holes if they exist, and extreme mass ratio, in spirals, small objects spiraling into supermassive black holes, mapping the space-time around them in exquisite detail. Next-generation ground-based detectors. The Einstein Telescope in Europe, Cosmic Explorer in the US will observe stellar mass black hole mergers with unprecedented precision. They'll detect thousands per year instead of dozens. They'll test general relativity to parts per million accuracy. X-ray telescopes will map matter flowing onto black holes, studying the physics of accretion and jets. Optical telescopes will track stars orbiting a star, testing general relativity and searching for deviations that might reveal quantum gravity effects. Future telescopes might detect Hawking radiation, though this is extremely difficult since it's so faint. Or we might create microscopic black holes in particle colliders. If certain theories of quantum gravity are correct, every new observation is a chance to test theory, discover surprises, push our understanding further. We're in a golden age of black hole astronomy. The next few decades will bring discoveries we can barely imagine. Quantum gravity. To truly understand black holes, we need quantum gravity, a theory combining quantum mechanics and general relativity. We don't have this yet. It's been the holy grail of physics for decades. Why is it so hard? Because quantum mechanics and general relativity seem incompatible. Quantum mechanics works with fixed space-time. Space and time are background stages where quantum fields operate. General relativity says space-time is dynamic. It curves, flows, ripples. Space and time are part of the physics, not separate from it. When you try to combine them naively, you get nonsense, infinities, contradictions, mathematical breakdowns. String theory is one approach. It proposes that fundamental entities are one-dimensional strings rather than point particles. Strings can vibrate in different ways, and each vibration mode is a different particle type. String theory naturally includes gravity. One vibration mode of a string is the graviton, the quantum of gravity. So string theory is automatically a quantum gravity theory. But string theory requires extra dimensions 10 or 11, not the 3 spatial dimensions we observe. The extra dimensions must be curled up at tiny scales, invisible to current experiments. String theory also lacks direct experimental confirmation. It makes predictions, but mostly at energies far beyond current colliders or length scales far smaller than we can observe. Alternative approaches exist. Loop quantum gravity, which quantizes spacetime itself, creating a granular structure at tiny scales. Causal set theory, which treats spacetime as a discrete set of events, and others. None are proven. All are active research areas. Black holes are where quantum gravity matters most. At singularities, quantum effects and gravity are equally important. You can't ignore either. A quantum gravity theory is required. When we have quantum gravity, we'll understand singularities. We'll resolve the information paradox. We'll know if black holes can tunnel to other universes, if wormholes are possible, if time travel is allowed. We'll understand the Big Bang, which was also a singularity. We'll know if the universe began or if something came before. Quantum gravity is the key to understanding the universe's most extreme phenomena. Black holes are pushing us toward it. Artificial black holes. Could we create black holes artificially? In principle, yes. Compress enough matter into a small enough space, and it collapses into a black hole. In practice, it's extremely difficult. To create even a microscopic black hole requires concentrating enormous energy in a tiny volume. Particle colliders smash particles together at high speeds, creating brief high-energy conditions. If you could collide particles at energies trillions of times higher than current colliders achieve, you might create microscopic black holes. These would be tiny subatomic scale and would evaporate instantly via Hawking radiation. They'd exist for less than a trillionth of a second, before vanishing in a burst of particles. Some worried that the Large Hadron Collider might create mini black holes that would grow and destroy Earth. This fear was unfounded. Even if LHC created mini black holes, it probably can't. The energy isn't high enough. They'd evaporate immediately. Hawking radiation prevents small black holes from being dangerous. The smaller the black hole, the faster it evaporates. A black hole the mass of a mountain would evaporate in seconds. One the mass of a car would evaporate instantly. Microscopic ones vanish before they can do anything. For future civilizations with advanced technology might create black holes deliberately. Reasons: energy extraction. Drop matter into a small black hole and harvest the energy released. This is more efficient than nuclear fusion. Computing. Black holes are the universe's ultimate information storage devices. You could use them as computers or data banks. Propulsion. A black hole could power a spacecraft by ejecting Hawking radiation or by dropping matter in and using the released energy. Wormhole creation. If wormholes are possible, maybe you could engineer them using artificial black holes. We're nowhere near this capability, but it's not forbidden by physics. Advanced civilizations might routinely create and manipulate black holes. If we ever achieve this, black holes would transition from exotic cosmic phenomena to technological tools. Philosophical implications. Black holes raise philosophical questions beyond physics. What is existence? Black holes show that existence has layers. Matter exists, but it can be hidden behind event horizons. From outside, infalling matter seems to stop at the horizon. From inside, it continues falling. Which is real? Existence becomes observer-dependent. What exists for you might not exist for someone else in a different gravitational potential. What is identity? If you fell into a black hole, would you still be you at the singularity? What if your information is encoded on the event horizon? Is that you, or a copy? What is causality? Inside black holes, causality breaks down. All paths lead to the singularity. You can't avoid the future. Time becomes space-like. Space becomes time-like. What is knowledge? There are limits to what we can know. We can't observe inside event horizons. We can't prevent information from falling in. Some knowledge is fundamentally inaccessible. This is epistemological humility, accepting that reality contains unknowable aspects. Not unknown because we haven't figured them out yet, but unknowable because they're hidden behind horizons we can never cross. What is destruction? If information falling into black holes is truly destroyed, that's profound. The universe can erase parts of itself permanently. Nothing is safe from ultimate annihilation. But if information is preserved somehow, that's equally profound. It means the universe won't let anything be truly destroyed. Information is sacred, conserved no matter what. We don't know which is true, but black holes force the question. What is meaning? In a universe where everything ends in heat death, where black holes evaporate and entropy maximizes, what matters? Some say nothing. Meaning requires permanence, and nothing is permanent. Others say meaning is in the journey, not the destination. We exist now. We experience, love, create, discover. That's meaningful regardless of the far future. Black holes embody this. They're temporary, they evaporate. But while they exist, they shape galaxies, process information, challenge our understanding. They matter even though they don't last forever. Living with mystery. After everything we've explored, here's the truth. We don't fully understand black holes. We know a lot. We've observed them, tested theories, made predictions that came true. We understand their exteriors, their gravitational effects, their role in the cosmos, but their interiors remain mysterious. Singularities are unsolved. The information paradox is unsettled. Quantum gravity is unknown. Some mysteries might be unsolvable. Event horizons hide information permanently. We can't send probes and retrieve data. We can't visit and return. This is frustrating for scientists. We're used to solving problems, unraveling mysteries. Black holes resist. They keep secrets. But there's beauty in mystery. Not every question needs answering immediately. Some mysteries are worth living with, worth pondering, worth keeping alive. Black holes inspire wonder. They're so extreme, so alien, so far beyond everyday experience that they remind us how strange the universe is. They inspire humility. We're clever, but not that clever. We've figured out a lot, but not everything. Reality contains phenomena beyond our current grasp. They inspire curiosity. Every answer about black holes opens new questions. Every observation reveals new puzzles. The more we learn, the more we realize we don't know. This is what science should be, not a march toward complete knowledge, but an endless exploration where each discovery reveals new horizons. Black holes are horizons in the literal sense, boundaries beyond which we can't see. They're also horizons in the metaphorical sense, limits of our understanding, inviting us to push further. Maybe we'll never understand singularities. Maybe the information paradox will never be fully resolved. Maybe quantum gravity will always be just out of reach. Or maybe the next generation will crack these problems. Maybe someone reading this will make the breakthrough. Either way, the journey is worthwhile. The questions are profound. The mysteries are real. And black holes impossible, terrifying, beautiful will continue challenging us, inspiring us, showing us the universe's most extreme face. Final thoughts. We've journeyed from the basics of black holes to the edge of physics and beyond. From event horizons to singularities, from Hawking radiation to the heat death of the universe. What should you take from this? First, the universe is stranger than you think. Black holes exist. Places where time stops, space tears, physics breaks. Not in science fiction, but in reality. Second, we're making progress. We've photographed black holes, detected gravitational waves, tested general relativity, extreme conditions. We're not helpless before these mysteries, we're actively exploring them. Third, limits exist. Some things we can't know, can't observe, can't reach. Event horizons hide information. Singularities break our theories. The far future is beyond our influence. Fourth, questions matter. Even without complete answers, asking deep questions about time, information, reality pushes our understanding forward. Black holes force us to think deeply. Fifth, perspective matters. Black holes put everything in context. They're places where stars die, where matter vanishes, where the universe's ultimate fate is foreshadowed. Against that backdrop, our lives are tiny, but our ability to understand black holes is remarkable. We're collections of atoms studying the places where atoms are crushed to nothingness. We're temporary patterns of matter contemplating eternal structures of spacetime. We're conscious beings exploring the universe's unconscious extremes. That's extraordinary. Black holes are the universe's ultimate challenge. They dare us to understand them. They test our theories, our observations, our concepts. We haven't fully met that challenge, but we're trying. And the attempt is making us smarter, more curious, more humble. Thank you for joining me on this journey beyond the event horizon. Keep looking up. Keep asking questions. Keep being amazed by the universe's most extreme objects. And remember, somewhere out there, right now, Matter is falling into black holes. Stars are being torn apart. Event horizons are growing. Hawking radiation is being emitted. The universe is active, extreme, mysterious, and we're part of it, the part that can observe, understand, and wonder. That might be the most remarkable thing of all. We've reached the end of this journey through one of science's deepest mysteries. If you've stayed with me this far, thank you. This has been a long exploration, a question without easy answers. But I think asking the question is valuable even without answers. Let me leave you with a few thoughts. Stay curious. The Fermi paradox reminds us how much we don't know. The universe is full of mysteries. Don't be satisfied with easy answers or comfortable certainties. Keep asking questions. Support the search, whether through donations to SETI programs, participation in citizen science projects, or simply staying informed. You can contribute to humanity's search for life beyond Earth. This is a collective endeavor. Think long-term. The Fermi paradox raises questions about civilization's survival and trajectory. What we do in the next century matters. Will we be wise enough to survive our technological adolescence? Will we spread beyond Earth? Will we eventually become one of the civilizations others wonder about? Appreciate Earth. Whether we're alone or not, we're currently the only life we know of. This pale blue dot is precious. Treat it accordingly. Take care of our planet and each other. Share the wonder. Talk to others about these questions. Share videos like this. Get people thinking about our place in the cosmos. The more people who care about these big questions, the better our chances of finding answers. Let me know in the comments. Do you think we're alone? What's your favorite explanation for the Fermi paradox? What should we do if we receive an alien signal? If you enjoyed this deep dive into cosmic mysteries, subscribe for more content exploring the biggest questions of science and philosophy. Share this video with someone who needs their mind expanded. And keep looking up. Keep wondering, because whether we're alone or not, the universe is vast and strange and beautiful. And we're lucky enough to be here, conscious and curious, able to ask these questions. Where is everybody? We don't know yet, but we're still searching, and maybe, someday, we'll find out. Thanks for watching. Until next time, stay curious. Let's do a thought experiment. Imagine that tomorrow, a radio telescope detects an unambiguous artificial signal from a star 40 light-years away. The signal is clearly structured, mathematical, information-rich. It's not natural. It's not terrestrial interference. After months of verification, the scientific community agrees. It's an alien message. What happens? Immediate reaction. The news spreads instantly. Within hours, everyone on Earth knows. Social media explodes. Traditional media covers nothing else. Governments make statements. Religious leaders respond. Stock markets might swing wildly as people process the implications. Decoding attempts. Linguists, mathematicians, and computer scientists work to decode the message. Even if aliens try to make communication easy starting with basic math, moving to more complex concepts, it takes time. Months or years of analysis might be needed to understand the content. Philosophical impact. Humanity's self-perception changes overnight. We're not alone. Other minds exist out there. This validates decades of searching. It proves intelligence isn't unique to Earth. Religious and philosophical systems grapple with the implications. Practical questions. Should we respond? If so, what do we say? Who decides humanity's message? These debates are contentious. Some argue for immediate response. Others urge caution. There's no global consensus mechanism for making this decision. Scientific revolution. Contact would revolutionize multiple fields. Astrobiology obviously, but also evolution theory showing life's development elsewhere. Linguistics, alien communication methods, sociology, how civilizations develop, and physics if the message contains scientific information. Long-term changes. If the signal is from 40 light-years away, any conversation would take 80 years per exchange. This is slow but manageable. Over decades or centuries, we'd gradually learn about each other. Cultural exchange would happen at the speed of light. The civilization that sent the signal might be dead by now. 40 light-years away means we're seeing them as they were 40 years ago. But even contact with an extinct civilization would be meaningful. Their message would tell us about their science, culture, and existence. Or maybe nothing changes much. After the initial excitement fades, life goes on. People still need to work, eat, sleep, The aliens are too far away to affect daily life directly. Contact becomes background knowledge, important but not immediate. Like knowing about quantum mechanics or black holes fascinating, but not life-changing for most people. Which scenario plays out depends on the message's content, how we respond, and how sustained the contact becomes. The meaning of silence. Let's return to where we started. To silence, we've explored many possible explanations. Some optimistic: we're early, they're hiding, they transcend it. Some pessimistic: they're rare, they self-destruct, the universe is dangerous. But there's something profound about the silence itself, regardless of its cause. The silence forces us to confront our isolation, whether temporary or permanent. We're currently alone in our ability to observe and understand the universe. No one is sending us answers. No one is guiding us. We're on our own. This is both terrifying and empowering. Terrifying because we bear full responsibility for our future. No one will save us from our own mistakes. Empowering because it means our choices matter. We're not following a script written by older, wiser civilizations. We're writing our own story. The silence also forces us to value what we have. Earth is the only known planet with life. Consciousness might be incredibly rare. If we destroy ourselves or our planet, we might be extinguishing something precious and unique. This should make us more careful with our civilization and our world. Not because we're cosmically important in some supernatural sense, but because we might be rare in a natural sense. And rare things deserve protection. There's also beauty in the silence. The universe isn't crowded with chatter. We're not just one voice in a noisy room. When we make our observations, develop our theories, create our art and culture, we're doing something potentially unique. Every human achievement, every scientific discovery, every work of art, every act of kindness might be unparalleled in our cosmic neighborhood. That makes these achievements more meaningful, not less. The silence is also an invitation. It invites us to keep looking, keep wondering, keep trying to understand. The mystery remains open. The question hasn't been answered. There's still discovery ahead. And maybe, just maybe, the silence will break someday. A signal from the stars, a message from minds utterly different from our own. And then everything changes. Until then, we live with the question, where is everybody? We don't know. But we're still here, still asking, still searching, and that might be enough.